All right, we're back. Studying exponential functions. We're back to the fun in math. How about that? Because I'm hooked on math. By the way, most of the math club members are seniors. If you're interested, we have a lot of fun doing math. It's pretty laid back. For math club, like we do every 2 weeks, we do a math competition at lunch, and every other 2 weeks we just kind of hang out. And then you miss 2 days of school year. That's math club. Okay. So yesterday was a lot of fun. We got to miss school. We got nice, neat, free T-shirts. They're mint green this year. So I feel bad. This is my pitch. In April, we get to go to Colorado Springs for a night. It's a lot of fun. Okay, again.
Don't say I can take it.
An exponential function has the variable as an exponent. To start, these are actually really easy to graph. They all pretty much have the same shape, and they all pretty much have the same y-intercept unless you change it, of course. So when I ask you to do the table, Sean, what did you get for -2?
25. 0.5.
Okay, stop. Sapphire, what'd you get for 0? Right. Okay. Key term there. Anything to 0 power is 1. Anything. That's why they all have the same intercept. Okay, unless you add something on there, like families of functions. Listen, what'd you get for the other 2? Number 1? 1? No. 2 to the first power. 2 and 2 to the second power. Okay. Let's graph that function. There's that curve, y equals 2 to the x.
All fancy.
Very. They all pretty much follow the same shape.
That'd be it.
Calls me.
They're just we're going to follow the same procedure as we did with families of functions. We were pretty good at that. So notice that the y-intercept here. So if I want to make this steeper, 4 to the x is going to go up faster. What's 4 squared? 16, right? You see how much faster these accelerate if the number is bigger. The nice thing is they have what's 4 to the 0 power. It's 1. They still cross at the same y-intercept. They just boom. Fast. I'll show you that. So this one would look like.
I can see that.
Okay. So that's. Now, what happens if I do this? Yeah, it's families of functions. You just drop it down 1 unit. So the new asymptote. This is an asymptote that never touches the x-axis here. So now we're at -1, and our intercept is 2 to the 0, 1 minus 1. And there's that. So you can move it up and down by adding or subtracting off the end. And how would I move it left or right? Any ideas? What do you pair a number with to move it left or right? With the x, right? So if I did this, which way is it going to move? Left 1. Right. So the new y-intercept is here. Or this new point is here. The y-intercept 0 is now 2. And you can see that matches up with this point, right? And then the asymptote is still the x-axis. It just doesn't come down to it. So use your families of function knowledge there to move things up and down and left and right. Okay. If you're a biologist, population growth here is pretty big in the animal kingdom. When you get, can populations grow on forever? Obviously they can't, because the carrying capacity of the, let's say it's a deer population, the carrying capacity of the forest is only so many deer, right? So they will eventually start starving and dying off. Okay, so in reality, you're going to see an exponential curve out. If there's enough feed to support the entire population, and then there aren't any predators, obviously. But then the predator population will probably increase, and the feed will not become as available. So you actually end up with something that looks like this. It's called a logistic curve. When I studied calculus. So the carrying capacity is this top asymptote. It's really neat stuff, but that's just kind of one way we can use exponentials. Okay. So population growth, and then eventually, obviously, it will level off. Sometimes if the predator population grows really high, the population of deer would drop, which is what we're experiencing in Colorado right now. The deer population is really hurt. I think 1965 or 70, there were about 4 million deer in Colorado. Now there are like between 1 and 2. So can you imagine 3 times as many deer being on the highway? Yikes, right? So there's your little tidbit. Conversely, bear populations have exploded. Right? Predator, bear's a predator, deer's prey. There's a little relationship there. Let's talk about exponential decay. You guys heard of carbon-14 dating?
Yeah.
Okay, this is the model that they would follow for that. If you have a fractional base, it causes a decay model. Remember, you can always graph anything with the table. If you're stuck on graphing something, try a table. Okay. What is 1/2 to the -2? What do you do with a fraction that's a negative exponent? Yeah, you flip it. So it becomes 2 squared, which is 4. That was one of those properties and powers that I was making sure you knew. This one would be 2. Still 1. And this will be 1/2. And this will be 1/4. Remember, that is 1 squared over 2 squared, right? 1/4. So you can rewrite these as such. And then graph it. Well, that is correct. General sketch, there you go. That's the decay. We call this exponential decay. So like I said, the dating methods we use in archaeology and science follow that model. Every so often, there's a half-life of some substance that puts off radioactive signature and it decays by half over so many years. I do want to caution you that a lot of those dating methods have their issues and their errors. Okay, so if people are using those methods, they have to make sure they're using it properly or you'll get a date that's incorrect. So be careful with that. Like carbon-14 is affected by water. That could be a problem in the world, couldn't it? Yeah, so be careful there on how you use those dating methods if you get to that point where you're using them. Okay. Any other possible areas we could use that? Anybody have any ideas? The deer populations in Colorado, right? Are we ever going to reach 0 deer in Colorado?
No.
Probably not. Hope not.
Possible.
Yeah.
Cause some issues system-wide, I think, right? Okay, so that's your basic exponential growth and decay graphs. Okay, they're pretty straightforward. Just remember the general shape, where to place it, and then you can move it up and down, left and right. Here is kind of another real example. How many of you drink coffee or tea? Yeah, me too. Okay. So, have you ever heard of Newton's law of cooling? Okay. This was actually an AP calculus question for the 3 responses last year, or 2 years ago. So,
Did you just take the AP test?
what?
Did you just take the AP test?
Not at the actual exam. I took the mock last year. Yeah, the mock exam last year, I didn't do it. Just for kicks. 3 years ago, I probably wouldn't have done very well on that test. Now I'll almost get 100%. I wouldn't get 100% guaranteed. So pretty close. Every year they see about 5 or 10 students who get 100% on that test. That's impressive.
Yeah.
Okay. So Newton's law of cooling is the difference between the temperature of an object and surrounding decreases in time. Okay, so you have the amount of cooling of an object. Okay. In our case, we're going to say coffee. Okay. So if we have a coffee, we do a lot of this stuff in centigrade. Okay. That's 95 centigrade. It's very hot.
Yeah.
Okay. Kind of the rule of thumb is double it and add 32. So that's pretty much almost around boiling point. Right, 100 centigrade is boiling, so we're pretty close to that. I'm not going to drink that cup of coffee for a couple of hours. Depends on the beverage container you have. And the room is 20 degrees centigrade. Okay. We can model this with this equation. You could graph that if you wanted to. What does this do? If x, think about x is 0, this is 1, right? That becomes our y-intercept. It's called the starting point in this case. Right? So times 0, what happens? How much? Does the coffee cool in 10 minutes? Sure. So this gives us the amount of cooling over it per minute. Right. So how would I solve that problem? Yeah, it's basic. It's a word problem, so it's a little bit more thinking involved, but plug 10 in. Oh, that's 10. Plug 10 in. What do I tell myself?
You have as responses all of this basically word problems, or you're gonna have one where you have to like write it out and explain each step.
I give you a summary after we're done. What do you got? 0.875 to the power of 10. You know how to put that in your calculators.
149 times 10 to the power of 8.
Times 75. How much? Somebody's got it. I don't have a calculator.
You think it's in 3.
It's probably drinkable now, right? The temperature at this point is 95 minus 19.73, so 75.27. A little bit better. Probably won't scald you if you look at it. Good. So just there's an application problem for you. Any questions? Okay. I am.
Let's see.
67.
Yes,
95 minus 20 is 75. Starting amount of cooling.
Never mind.
We'll check this Tuesday. Just want to make sure you got it so we can do the harder problems Tuesday. Yeah, and it'll make sure that you have less work in the night too. So give you the weekend. I'll go over example 3 and 4, a beekeeping example and a finance example. Lots of applications for exponentials. If you start a savings account now, and put away, let's say you start at $10 a month right now, and when you get working like my age, you're putting in $100, $500 a month, your growth will actually follow this exponential curve. No, it's a lot more shallow, but I'll show you an example of that. The advantage of starting now is that $5,000 you have when you're 20, that gains interest every year. So, if it's a 5% interest, you're earning $250 a year as opposed to 0 if you don't have any. Suggestion. I didn't do it when I was your age. Okay. Here you go. Any other related rates?